So as we start thinking about acids and bases, we really need to get a handle on their concentration. So how much acid or how much base is in a specific solution, whether it's the bloodstream, whether it's in an IV bag, whether it's in a beaker, doesn't really matter. So when we measure acid, which is really H3O plus because that's H plus attacked by water, we need to have a comparison of how much OH negative. Because if we have more H3O plus than hydroxide, then we're going to be more acidic. The opposite's true. If we have more hydroxide than hydronium, then we're going to be basic. Neutral is when we have the exact same amount of H3O plus as we do hydroxide. So if we were to look at pure distilled water, straight from the store, untouched, unopened, carbon dioxide can dissolve into water and make it slightly acidic, which is the issue with buying it and then opening it. But let's pretend a perfect world, and when we open up pure water, it has equal amounts of hydronium and hydroxide. However, this number is tiny. But we use this number to compare all other solutions, which is the important part. So when we say 1 times 10 to the negative 7, that's really 0.00000001. Capital M is just a concentration unit. We'll see it in week 15. So it's just a unit, don't worry about it, but this is tiny. This is basically in the millionths, right? The tens of millions, the hundreds of millions kind of small scale kind of number. So really it just says water stays water most of the time. But when water has to, it can break apart into ions and conduct a little bit of electricity. This is what makes water dangerous with, say, electricity. So the ability for water to attack water is there. It's just tiny. Most of the time, that arrow to the left being the bigger arrow, most of the time water stays water. But when water attacks itself, we use those same definitions that we just saw. This hydrogen was donated to this oxygen. So these electrons basically went and got it, would be another way to think about it. So that's the electron pair donor, the electron pair acceptor of the Lewis definition. But in the end, we have a teeny amount of this one, and then we have a tiny amount of this one. So it's not much, but it is something. And it's a comparison of these numbers that we determine all acidity and basicity for solutions. So it doesn't happen much. That's why this arrow is definitely to the left most of the time. Very little of the time does it go to the right. But if you were to add something to the water, you're going to tip this scale left or right. And the outcome of how much hydroxide and hydronium you have left over after stirring, that's how we determine our acidity and basicity of our solutions. So an acid solution is one that has a large amount of H3O plus. So 10 to the negative 6, 10 to the negative 5, 10 to the negative 4, 10 to the negative 3, all the way up to 1. That means that hydroxide for an acidic solution is going to be pretty small, like 10 to the negative 8, 10 to the negative 9, 10 to the negative 10. So those negative numbers, those negative exponents getting smaller means there isn't much of it. And then a basic solution is the opposite. Hydroxide is going to be big. It's going to be in a large concentration. So 10 to the negative 6, 10 to the negative 5, 10 to the negative 4, all the way up to 1. And beyond, those are very basic solutions. And if base goes up, acid goes down. It is a scale. And as you tip one, you're going to tip the other. So Kw is our starting point. If we were to multiply H3O plus times hydroxide, you're going to multiply 1 times 10 to the negative 7 times 1 times 10 to the negative 7. And when you multiply exponents, it's the same thing as adding them. So really, negative 7 and negative 7 become negative 14. And this is the dissociation constant for water. So if we have 1, we can calculate for the other, just using a little bit of algebra. Just remember that acids are high in hydronium, bases are high in hydroxide, and we can look at that answer and see it both ways. So if multiplying exponents is like addition, then dividing exponents is like subtraction. So if you were given one of either hydronium or hydroxide, you could solve for the other using some algebra. So let's try an example. Here we have H3O plus is 1 times 10 to the negative 5. So let's say this is, some apple juice that we bought at the store. We tested it, and this is what it shows us. How do we know if that's acidic or basic? Well, the first thing that we can do is realize that 10 to the negative 5 is larger than 10 to the negative 7. A lot of students don't like that idea because they hate numbers, and I'm not a huge fan of them either, but 1 times 10 to the negative 5 for H3O plus, which is acid, that's 0.00001. So 10 to the negative 1, negative 2, negative 3, negative 4, negative 5. We were comparing it to 1 times 10 to the negative 7. That was neutral. And that would be 0.000000 and then 1. So this is basically 100 times stronger, 100 times more acidic because of its H3O plus kind of number. They also want us, in this case, to calculate hydroxide concentration. So we have the formula for that. That's Kw. Kw is 1 times 10 to the negative 14. And that's what happens if we multiply any acid concentration in water times any base concentration in water. Now we know that H3O plus is 1 times 10 to the negative 5. So if 1 times 10 to the negative 14 is always the product, then 1 times 10 to the negative 5 times hydroxide, or if this were algebra, we could just call that X, is the answer. In algebra, if we want to get rid of hydroxide, we're going to have to, or at least get hydroxide by itself. We're going to have to get rid of this number. If it's being multiplied, the only way to get rid of it is to divide by it. They will cancel. But in algebra, what you do to one side, you have to do to the other. And then what you have in this situation is division of exponents. That's really just 14 subtract 5. So the answer then is hydroxide is just 1 times 10 to the negative 9. Again, capital M is just a concentration unit. This also tells us that this is a tiny number. This would be 0.0000000, so negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9. So because this is tiny and this is base, that tells us that this being acid, both definitions say that there's a lot of acid. Because if there's a tiny amount of base, there must be a whole lot of acid. Because we've tipped that scale so that acid is now high, base is low. And that's what we're after in a couple of our math problems of this chapter. There isn't many, but there is enough to be worried about. So those numbers are kind of hard to think about, right? They're powers of 10, and you have to worry about negative exponents. When negative exponents get bigger and more negative, they get smaller, and when positive exponents get bigger, they're actually bigger. So that's difficult for some students. So what scientists decided to do was, let's make it a little bit easier to think about by removing the powers of 10 and just making them normal numbers. But in order to do that, we have to change our equation. So if we have this power of 10 issue, the only way to get rid of it is to use the log function. And if we have a negative number, we're going to have to get rid of it by making it negative. So 2 negatives make a positive, and then log is the function of base 10 power, so we can get rid of a power of 10 that way. So long math problem now short, really what we're seeing as a relationship of pH is hydronium's exponent is really the pH number. So really this number is just the power of 10, or a relationship to it. And that's a way to make these numbers that are a little creepy look a whole lot more normal. And that's pH in a nutshell. It's a power of 10 function. So as you go from pH 3 to pH 4, you're becoming 10 times less acidic or 10 times more basic in a sense, even though you're still in the acid side of the scale. But that's how to relate the numbers we just saw to the numbers you've probably heard about, and that's pH. So you can imagine that this is a scale, right? As one goes up, the other goes down. So neutral is what we mentioned earlier, and that's right in the middle. So neutral is when acids and base concentrations are equal, and because H3O plus gives you pH, you can imagine that if we see a 7 over here, we're going to say a 7 over here. The pH of your stomach is around 1, so that'd be 10 to the negative 1, and that's where we get a pH of 1. What they're not showing us is something that could be useful, and that's that if you multiply these two numbers together, you get that 1.0 times 10 to the negative 14 kW kind of number. But something that can be pretty valuable is to realize that pOH is really just a relationship of OH negative. So if you add these two together, instead of multiplying, you're going to get 14. So what that tells us is if this is 13, then this is 13. Because we would have taken its negative log to get rid of the power of 10 to get rid of the negative. So this 7 for OH is really this 7 for pH. And this would be 8, 9, 10, 11, 12, and so forth. So it's just the opposite. That's what we're trying to show you. So you can imagine this is now 6, 5, 4, 3, 2, and 1, and 0, and so forth. So pOH and pH is a whole lot easier because addition and subtraction is a whole lot easier than multiplication in your calculator using scientific notation kind of set of numbers. So just remember as a result that any numbers down, doesn't matter the scale. So if you have a tiny amount of acid, if you have a large amount of base, if you have a high pH, if you have a low pOH, that's all basic. And then as you go up for acid, a large amount of hydronium, a small amount of base, a low pH, or a high pOH, that's all acidic. And you'll see those kinds of definitions at the end of your matching section of your homework. So notice as one goes up, the other goes down. That works for hydronium versus hydroxide, but it also works for pH versus pOH. So if we have a problem with H3O plus, then we have to figure out how to solve it, right? They want pH. So when we think about this problem, we have to think about, well, the only formula that we've seen so far is that pH is the negative log of the acid, which is H3O plus. This problem says, what is this number? So if 12.2 equals the negative log of basically x, if this were algebra, that is a mess. How do we solve that mess? Well, in order to get rid of negative, we're going to have to do the reverse of what we just did, and that's make the other side negative. So negative of the right makes it, positive, and negative of the left is now negative. In order to get rid of log, we have to take the power of 10. And now we're ready to throw this into our calculator. This is really just the anti-log button of your calculator. 10 to the negative 12 will give you the answer. Notice this number here is like 1 times 10 to the negative 12, but because of that 0.2, it's not going to be perfect. So it's going to be within that negative 12, negative 13 kind of range that we're about to see. So here it's 6 times 10 to the negative 13. So this is not one that you can do in your calculator or in your head. You're going to have to use a calculator because it does have a decimal for the pH. It's not as easy as just saying that this number is 12. If this number is 12, then we can say 12, and that's great. But when it's 12.2, it's actually going to have some leftover, and that's what we're seeing here. That's what we have to worry about. So really, as long as you can use your calculator and you know the formulas, which you're given those on the test, you should be pretty safe. So this is what you're given on the test. This is also what you're given in our lab and some of our extra credit. You have to be able to know where you're at and then how to get there. So what we just saw a moment ago was we had a 12.2 pH. They wanted us to go to H3O plus. So then it shows you the formula that it's required to get there. So in your calculator, you take 10 to the negative power of 12.2, and then you get the answer. So really what we need to do then is just know the calculator buttons in order to make that work. So basically in this chart, if you're going up or down, those are the same kinds of problems, whether it's pH or OH, doesn't matter. Just be careful which one they mention to know which, if you're dealing with base in the OH or the acid in the H to H3O plus kind of realm. If you're going up on the calculator, if you're going up, this is going to be something that we're looking for. Get the right kind of marker there. This is going to be the negative button, so that's a plus minus button. And then you're going to have the log button. And then you're going to have the number, which is going to be some kind of number. And then you're going to have to do the second button. And then after you do the second button, this is going to give you the power of 10. You're also going to need the x to the negative 1. That'll give you access to the EE button. And then you can put in your negative power of whatever. So negative log number, that number just requires the use of exponents. And the easiest way to use exponents without doing the little rooftop buttons and all the other buttons that have to require parentheses, if you use that x to the 1 button, this EE exponent feature is definitely your friend. If you're going down, a little bit easier in your calculator, down is going to be second button, log button, because that'll give you access to 10 to the negative power of. We just need to say negative, so plus minus, and then your number. Sounds a little bit easier to deal with, and because calculators can be tricky and all calculators are different, we do show you the TI-30X2 in class in our experiment. So that'll help out too. But really it's just a matter of using your calculator. It's either negative log number up or second log negative number down. That's the idea. As we look at the pH scale, we need to know how it applies. And we'll see this in our other acid-base lab, and that's that stomach, lemon juice, all very acidic, lemon juice being very sour, grapefruit being very sour, sauerkraut being very sour, wine being very sour because of its acidity. A lot of that alcohol can turn to acetic acid, so get that vinegary kind of smell if it's been there sitting too long. Tomato juice, very good for eliminating the thiols of, say, skunk spray, which are very basic. Coffee and rainwater, so the ability to dissolve carbon dioxide makes rainwater acidic, and then coffee bad for your teeth, much like soda. Bad for your teeth because of the phosphoric acids and so forth that are in them. We get to urine that is slightly acidic, but even at 6, it is has enough base, so to speak. It's got enough ammonia in the urine in order to neutralize, say, a jellyfish sting or something like that. That is true. Milk, a lot of people drink it for an upset stomach, and that's because your stomach acid is 1. So even by adding some fatty acids that are, say, around 6, that's still more base available than the acid that has very little base available because it has so much acid available. Human blood and pure water, really close. Human blood around 7.35 or so. We get into a lot of protein like the egg whites, a lot of baking soda. milk of magnesia, which is in a lot of your Rolaids and TUM and acids. And then your really slippery ones like ammonia bleach and oven cleaner, they're at the bottom. So we'll see a lot of this and practice a lot of this in lab with cabbage juice specifically to prove that their pHs are what they're shown. You can also imagine that your body is a lot like plants. We're based on the same kind of organic atoms in the end. We're all carbon containing. And if we are too acidic, we tend to be too unhealthy. So having a good basicity in our body allows us to be a little bit healthier, and that's also true for plants. Plants like to be a little acidic to neutral, and our body's, again, a little basic. So there's a little bit of difference there, but you can add fertilizer, get them, pretty safe in the basic side. As long as you're not too basic, then you start killing the grass. And the same goes for acidity. Too much acidity can kill the grass as well, kill everything for that matter. So everything in moderation is the idea, but we do want to stay close to neutral. For our body, slightly basic is important, and for grass and your lawn to make it nice and pretty, slightly acidic is a little helpful. So in our last video, we'll come back and talk about how acids and bases interact in the form of buffers.